Our next presenter is Noah, and he will introduce his talk.
Yeah,
Thanks,
thank you.
Noah.
All right, thanks for being here, everyone. Yeah, so this past summer, I worked on the data-driven buoy deployment project in collaboration with Dani Jones and Russ Miller from CIGLR and Shelby Brunner and Joe Smith from GLOS. And then we had a little bit of inspiration from Paolo Paolucci at the University of Valencia in Spain. And just to get everyone in the right headspace, let's just take a moment to appreciate how far we've come with our observation network across the Great Lakes. This plot shows the total number of observations we've had over the past 13 years or so, and how many more we've been taking in recent time. So a little bit about me. I'm going into my junior year in computer science and mathematics at IU Bloomington. I'm from Noblesville, Indiana, which is a little bit northeast of Indianapolis, and I'm an aspiring machine learning engineer, and I'm super excited to be here. So, as I said before, our current observational network across the Great Lakes is fantastic. This here is a plot of the density of observations in areas across the lake mask. And I said it's fantastic because it's fast and very up to date, but as you can see, it's still a little sparse and there's always room for improvement. And so in the age of machine learning and artificial intelligence, it's really important that we look to improve on our network using these new tools. So I won't go too in depth here, but a little bit of background in how we train our models. So Gaussian neural processes, they take a number of context sets and a target set, with the goal being to map the context sets to the target set. And then they output a distribution of possible functions as well as uncertainty. And so this plot I have shown here, the orange dots are context points. The blue line in the middle is essentially the best function that our model could find to map to these context points. And then the highlighted region is the uncertainty. And so this is what makes it so, this is what sets it apart from other machine learning structures, is first that it can handle non-uniform data, so combining data from multiple sources and dealing with complex and variable data. But it also gives us an uncertainty metric automatically. And so this makes it a lot easier to sort of validate the results we're getting from training. So I'll reiterate, our goal is to develop a quantitative framework to inform the placements of the next generation of Great Lakes buoys, specifically with the goal of better understanding sea surface temperature variability. And the way we want to do this is by training models using Gaussian neural processes through the deep sensor framework and evaluating the results. So you might ask, what is deep sensor? It was developed in 2021 by the British Antarctic Survey and some collaborators. It's an open source Python framework, and it's currently hosted and maintained by the Turing Institute in the UK. And what does it offer? So the first thing that it offers in training is tasks. And so the idea of Gaussian neural processes is that you can upload a handful of context sets, but it's really hard to sort of input those into the model as is, especially if they're non-uniform and they're not on the same grid, or they're not taken in the same time period. And so tasks help separate all of these context sets and combine little pieces of them and make it easier to train the model off of. In combination with a data processor, it makes things really smooth using Deep Sensor's framework. Additionally, initializing a neural process is much easier using Deep Sensor. And then it offers a prediction utility. And so the plot in the upper right, the left side of that plot is predicted sea surface temperature on February 14th, 2018. And then on the right, remember the uncertainty metric I mentioned to you. This is a standard deviation graph. And so it shows where the model is less confident, making it a lot easier to kind of see which areas are struggling during training. Next, we have acquisition functions and the greedy algorithm. And so those first three utilities were used during model training, but we're talking about placing new buoys. And so we have a separate file called our active learning file, where we essentially evaluate our model and find areas that need the most improvement and then place buoys there. And so an acquisition function is the function that we're using to decide which areas need to be chosen. And so ours is standard deviation. So it lines up well with the standard deviation graph, because when we run our active learning file, we look through this grid and then we find the area that has the highest standard deviation. And that's why it's called a greedy algorithm, because it doesn't have future outcomes in mind. It just picks the highest standard deviation. And then I have a plot in the bottom here that shows you sort of what you can expect as an output of suggested buoy placements using our active learning file. So data usage. I talked about all these non-uniform context sets. So here's what we use. We use GLOSS for sea surface temperature. We used a bathymetry data set as well as a binary ice indicator. And these are the three most important data sets we use because we want to develop, or we want to inform our model of the covariance structure between these three in hopes that if it doesn't have enough information in any of them, it can sort of fill in the gaps and hopefully make good predictions from that. Additionally, we have a lake mass because there is no sea surface temperature on land. And we implemented a seasonal cycle system, which takes the sine and the cosine of the date of year. And then so that pair shows up once a year, informing the model of this seasonal cycle and the cyclical nature of years, essentially. And so, yeah, we don't just necessarily use all of this data. We have a couple sampling methods, and this is where a lot of the work we did, we spent a lot of time on this. And so one of the things we did was sample every single point on the lake mass. Another thing we did was pick an arbitrary number of random points at the beginning of training, and we trained the model just off those points on the lake mass and hope that it can fill out the rest. And then our last sampling method for training was picking an arbitrary number of random points and then re-randomizing during every epoch or every iteration of our training loop. And so, so this was in training, and it's an important distinction because we don't have to use the same sampling method in training and active learning. For active learning, we want it to give us good buoy suggestions for our actual network. And so we sampled about 280, 300 buoys. I don't remember the exact number, but we sampled real buoys so that when our model is evaluating, its training in active learning, it only uses the buoys we actually have and then places things off of that. And so we can have any combination of our training methods along with the active learning sampling. And so the plots I have up top are the context sets, and then the right plot is our target set, which is sea surface temperature, because that's what we want to map onto. And then here are the buoys we're using in active learning to sample. So time for some results. So during training, these are our three training sampling methods. The static random sampling is the worst. For those of you who don't know, these are methods commonly used in machine learning training. They essentially tell you how well your model is performing, and the goal is to lower them as best as you can. And so the static random sampling is performing worse than the other two. The dynamic random sampling is second best in this case. And then when we sample the entire lake mass, we not only converge, but we have extremely low validation root mean square error, meaning it's probably going to make great predictions. And as you can see here, we don't only look at these training metrics, we also look at their predictions. And so on the left, we have the static random sampling. There's not a great gradient of sea surface temperature here. You see a lot of yellow blotches. And if I included the uncertainty graph that comes along with it, you would see that these blotches have higher standard deviation. And so this does a very poor job of interpolating sea surface temperature throughout the lake mass. But then in the middle, this is our full sampling run. So we trained a model on all of the lake points. And as you can see, there's decent boundaries and good gradient of temperature. Now compare this to the graph in the upper right, which is taken straight from GLOSS. And you can see that our full sampling makes a prediction that's almost exactly the same. Now, dynamic random sampling, it's really interesting because it doesn't seem to understand ice cover, but fortunately that's not our goal. Our goal is to figure out sea surface temperature. And so for the sake of not misrepresenting the data, I included the color scale, which is much different than what it actually should be, because it's never negative 20 degrees Celsius in any of the lakes really. But where there isn't this negative 20 degrees Celsius ice cover, the temperature is actually quite accurate to the glossy data. And so we chose to keep this around. It's actually performing better than the static random sampling if you ignore the confusion surrounding ice. So you would think that the full lake mass sampling would perform the best, but one of the things we did with Paolo Paolucci was we sort of took his metric. What he did was he would plot the validation root mean square error during active learning against the number of buoys placed or acquisition iterations. And so as you can see at the top, the validation root mean square error is much higher throughout, and it actually changes a little bit less than on the bottom in the dynamic random sampling. And so this is because our model essentially is overfit when we sample the entire lake mask. And so when we switch down to our 300 buoys or so in active learning, it has no idea how to transition. It hasn't had to deal with so much empty space, and so it doesn't know what to do. Whereas in dynamic random sampling, our main run was we would randomize 500 points during training, and we would do that 50 times. And so every single training iteration, it would have to deal with this small number of points, and it would have to work its way around the lake. And so it's very comfortable using these 300 or so points. So even though the prediction was great for full lake mass sampling, the metric we use for active learning shows that it's not necessarily as good. And so here are the corresponding plots to these. On the top, we have this beautiful, well-distributed, great buoy suggestions, but we just can't really trust it because we don't like the metric. Whereas on the bottom, the metric's a little bit better, but as you can see, it really likes these tributaries and bays on the edge, and they're actually really near each other. And so we don't have a specific suggestion at this point in time, but we do know that the bottom is very telling, not only in how we can improve our model, but also areas that may still need some coverage. So before we get into moving forward, what have we accomplished? Deep Sensor actually does not have a metric for active learning other than just showing you like plots. And so we had to implement a metric with help from Paolo Paolucci. And this was very helpful because, we probably would have stuck with the full sampling, which we now know is clearly overfit, had we not had this metric. And it helps us kind of have a uniform way to compare how everything translates to active learning and buoy placement. Additionally, now we understand the trade-off between predictions and buoy placements. They don't necessarily coincide. And then we emphasize sampling efficiency versus accuracy. And so we find that the best active learning performers sampled a number, relatively similar to the 300 buoys in active learning. And so that the number of random points sampled needs to be close, but we also need to make sure they're not static because otherwise it relies on those static points too much. So moving forward, one of the main things we're going to start with is targeting the lake mass. And there's a number of different things we can do. I don't know how I'm doing on time, but I'll try and speed through this part. So one thing we can do is just make more precise edges, because if there's any land in the lake mask, then that could throw off the function that our model is deciding is best. And so maybe we just have this terrible function because there's a bunch of land in our lake mask. Otherwise, we can err towards the water side, because if there's a little bit of water excluded, I still think that would work out. Another thing we can do is mask out the tributaries and some of the bays that aren't in the proper lake mask. I'm not going to say these aren't important because they're very important to the coastal communities around them. But for our greater understanding of the entire Great Lakes, these tiny little spots on the edges don't give us that much information. Additionally, we're going to try and isolate each lake, and using the results that we have right now, we can hopefully prioritize lakes, because we know in pretty much every active learning run that I did, it was Lake Superior, Eastern Lake Ontario, and Lake Huron. So we're probably not going to need a new buoy in Lake Michigan or Lake Erie just yet. And then, so active learning metric is really great for comparing our active learning runs, but it doesn't quite tell us how great it will be in the actual water. And so it's not really a good physical representation. Validation root mean square error, it tells us how the model's performing, but it doesn't tell us the total gain. And so there's a number of different ways we can fix that. We have no idea at the moment what kind of metric would solve that problem, but maybe we'll get there. So for some broader impact, obviously greater coverage and better forecasting. One thing that we could do, the sea surface temperature prediction from full sampling was fantastic. And so maybe we could use that for some sort of forecasting. But in general, if we can place a new buoy and it's very efficient, then we're going to have better coverage, and we all know the benefits of that. Additionally, one of the points of this project was to make sure we're not taking too much redundant data. And so using this, we can hopefully not place buoys in places that we really don't need buoys, and we can be really efficient with the very expensive equipment we're putting in the water. And then it can prove scalable to broader oceanic applications and atmospheric ones. Paolo Paolucci is working on placing new aerosol sensors in the atmosphere. And that's obviously a wider geographical grid than the Great Lakes. How am I on time, Mary? Okay, thank you.
Okay, great job, Noah. We've got time for questions. Sure, John Doe.
Hey Noah, awesome presentation. Was just thinking this, like you mentioned that it was like Paolo Vellucci, and he did this for atmospheric aerosols, and you were saying that like possibly one of the issues that's like causing this active learning to recommend placements in like kind of these kind of random spots is possibly your lake mask. Does his project incorporate a kind of a lake, like some kind of mask, or is it more of like an open, like like it doesn't have like weird little sections, it's more of just a larger grid?
It's a larger grid, but he actually, they masked out the ocean, not because they needed to for model training, but they just can't put sensors there.
Yeah.
It's really interesting, honestly. I mean, that's a good point, because I don't know if he's had that problem. We had a lot of similar bottlenecks, even though we're doing drastically different research. So I don't have a great answer for you. Maybe the lake mask isn't the issue.
Awesome.
We'll figure
Thanks.
it out, though.
Questions?
So this is a little counterintuitive, but you had a slide that said, reduce costs, and it's like, could you use the same tools to look at the least useful buoys that exist now?
I mean, I don't see why not. Although it's not implemented in the deep sensor workflow, I'm sure you could use a lot of the similar utilities. I mean, like, what's a de-acquisition function, though? I mean, I honestly have no idea, but that's a really interesting point, right? Like, what is a redundant buoy? I don't know. Good question.
I've got a quick question. So the slide where the figure that you showed on your very first slide, and then again at the end with the number of observations by year, do you know, you very well might not, there's a pretty big jump from 2020 to 2021. Do you know if there were a lot more observing platforms put out during that time, or do you have any idea?
The Russ question. Honestly, I don't know. I wasn't around, and I only started. Oh, it's a Shelby question. Sorry.
So that was, we had a mini grant program in 2021, and we had a bunch of new, smaller, lightweight platforms that went live in 2022 and have sort of sustained and has had some increase. So that's where most of that jump comes from. I don't think it's all of the jump, but it's a big piece of it.
Yeah, that's kind of what I was wondering, if it was the spotter buoys.
I got a point to add. This is Joe Smith. Also in 2021, there were some platforms that increased the frequency of their observations. So we got like an order of magnitude more observations. Trying to build up like archival data sets became really difficult beginning that year. So yeah, big jump to do that.
Does make Russ's question of, redundant buoys or ones that aren't as helpful. That's a good question. Interesting to look at.
Aren't adding much information.
Yeah. Okay. There aren't any more questions for Noah? Okay, great. Well, we will move on to our next one.
Thank you, Mary.